Let me tell you something that will completely shatter everything you think you know about light, space, and reality itself. You've been told your entire life that nothing can escape a black hole, not even light. That's true. But here's what nobody tells you, and what will haunt you for the rest of this video. Light doesn't actually disappear inside a black hole. It's still there, right now, traveling forever. But here's the part that's going to break your brain. From the light's perspective, it never even reaches the black hole. Time stops. The journey ends before it begins. But from our perspective, we watch it fall forever, stretched and twisted into something that barely resembles light anymore. The same beam of light is simultaneously frozen at the edge of oblivion and already destroyed at the center. Both things are true at the same time. And if that doesn't make your head spin, wait until you understand what this means for every photon that's ever touched your eye. Because the implications reach far beyond black holes. They reach into the very nature of what you call, now, what you call real, and what you call you. Before we journey into the darkest places in the universe together, I need you to do something. Hit that like button right now. Because what you're about to learn isn't just information, it's a perspective shift that most people never experience in their entire lives. Subscribe and turn on notifications, because we're going deep into places that will change how you see literally everything around you. And tell me in the comments, where are you watching from, and what time is it where you are? Because the answer to that question is more relative than you think. Time is different for you than it is for someone watching this in another country. And by the end of this video, you'll understand why in a way that will genuinely disturb you. Let's start with something you think you understand. Light. You've been told light is the fastest thing in the universe. You've been told it's a wave and a particle. You've been told it has no mass. All of this is true. But here's what they don't emphasize enough. Light doesn't experience time. Think about that for a second. A photon leaves the surface of a star 10 billion light years away. From our perspective, it travels through space for 10 billion years before entering your telescope. 10 billion years. The rise and fall of galaxies. The birth and death of entire solar systems. But from the photon's perspective, zero time passes. None. The moment it's created and the moment it's absorbed are the same instant. This isn't philosophy. This isn't poetic. This is what Einstein's special relativity tells us mathematically. As you approach the speed of light, time dilation becomes infinite. At the speed of light, time stops completely. The photon doesn't experience anything because experience requires time. It exists in a timeless state where departure and arrival are simultaneous. Now, why does this matter for black holes? Because when we ask, what happens to light inside a black hole, we have to ask, from whose perspective? The universe is not a single story being told. It's countless stories being told simultaneously. All of them true, many of them contradictory. Let me give you a foundation that might surprise you. Black holes aren't actually holes. They're not tunnels to other dimensions. They're not cosmic vacuum cleaners sucking everything up. The name black hole is almost cosmically terrible marketing. What we're really talking about is a region of space where gravity has become so extreme that it warps space-time itself into a closed trap. Here's a better way to think about it. Imagine space-time as a rubber sheet. Put a bowling ball on it, that's a star, creating a dip. Now imagine compressing that bowling ball down to the size of a marble while keeping all its mass. The dip becomes a funnel. Keep compressing atom-sized, then smaller. Eventually, the funnel becomes so steep that the rubber sheet folds in on itself. That's not a perfect analogy, but it gets at something crucial. A black hole isn't a thing in space. It's a feature of space itself. The event horizon is the point of no return, the boundary where this folding becomes complete. And here's what's wild. There's nothing special at the event horizon itself. If you fell through it, you wouldn't hit a wall. You wouldn't feel anything change. You'd just cross an invisible boundary, and suddenly, every direction you could travel would lead deeper inside. Even moving up would take you down. Space itself has been twisted so severely that escape becomes geometrically impossible. Now let's talk about what makes black holes black. You might think they're dark because light can't escape, and that's true, but there's something deeper happening. Black holes are black because space-time inside the event horizon is structured such that all future paths lead to the singularity at the center. Not most paths, all paths. Every possible trajectory, no matter which direction you accelerate, brings you closer to the center. This is where your intuition breaks down completely. In normal space, if you're falling toward Earth, you can fire rockets and escape. You can change direction. Inside a black hole, firing rockets toward the singularity, away from it, or sideways, all of these actions lead you toward the singularity. It's not that the gravity is pulling too hard to escape. It's that away doesn't exist anymore. The geometry of space has been modified such that the singularity is in your future, the way tomorrow is in your future. You can't travel away from tomorrow. And light? Light always travels at light speed in its local frame of reference. But inside a black hole, even light traveling outward at full speed is actually moving inward toward the singularity. The space itself is falling inward faster than light can climb outward through it. Here's your first major mind-blown moment, and we're going to take our time with it because this is where reality starts getting genuinely strange. What I'm about to tell you was discovered by Carl Schwarzschild in 1916, just 1 year after Einstein published his general theory of relativity. Schwarzschild was a German physicist serving in the military during World War I, and while stationed on the Russian front, he solved Einstein's field equations exactly for the case of a spherical mass. What Schwarzschild found was this: there's a specific radius around any mass where time dilation becomes infinite. For a non-rotating black hole, this radius is called the Schwarzschild radius, calculated as r equals 2 times the gravitational constant times the mass, divided by the speed of light squared. For Earth's mass, this radius would be about 9 millimeters. For the Sun's mass, about 3 kilometers. If you could compress Earth down to the size of a marble, or the Sun down to the size of a small city, they would become black holes. But here's the stunning part that even many physics students miss. At the Schwarzschild radius, time doesn't just slow down. From an outside observer's perspective, it stops completely. Completely. If you watched a clock fall toward a black hole, you'd see it tick slower and slower as it approached the event horizon, and right at the horizon, the clock would freeze. The last tick would never complete. Now think about what this means for light. As a beam of light falls toward the event horizon, we see it redshift, its wavelength stretches, its frequency drops. It becomes redder and redder, dimmer and dimmer. At the exact moment it crosses the horizon, from our perspective, it's stretched to infinite wavelength. Infinite. It becomes quite literally invisible. Not because it's gone, but because we would need infinite time to see the crossing happen. So we've established that, from our perspective, light never quite seems to cross the event horizon. It gets stuck there, frozen in time, red-shifted into oblivion. But what about from the light's perspective? Or more accurately, what about from the perspective of an observer riding alongside that beam of light, falling into the black hole? This is where things get truly bizarre. And this is the question that kept physicist John Archibald Wheeler up at night in the 1960s. Wheeler, by the way, is the physicist who actually coined the term black hole in 1967. Before that, they were called frozen stars or collapsed stars. Wheeler understood something profound. The story of what happens depends entirely on where you're standing. From the perspective of the infalling light, or an observer traveling with it, the journey to the event horizon takes finite time. Not infinite, finite. You approach, you cross, you're inside. No drama at the boundary itself. For a supermassive black hole, like the one at the center of our galaxy, which has a mass about 4 million times that of the Sun, you could cross the event horizon without even noticing. The tidal forces there are gentle enough that you'd survive for a while. Think about what this means. The same event light crossing the event horizon takes infinite time from one perspective and finite time from another. Both perspectives are correct. Neither is more real than the other. This isn't a contradiction in physics. This is physics working exactly as Einstein predicted. Time is not absolute. There is no universal clock. The rate at which time flows depends on your motion through space and the strength of the gravitational field you're in. Let me give you an analogy that might help, though no analogy is perfect. Think of spacetime like a river flowing toward a waterfall. Far from the waterfall, the current is gentle. You can swim upstream if you're strong enough. This is like being far from a black hole. Light can escape easily. As you get closer to the waterfall, the current gets stronger. You have to swim harder to stay in place. And there's a point where even the strongest swimmer can't make progress upstream, but can still stay in place by swimming at maximum effort. This is like being near, but outside the event horizon light can't escape, but it can hover if it's moving directly outward at light speed. Then there's a point at the waterfall's edge where the water is flowing faster than even an Olympic swimmer can swim. Past this point, everyone goes over the falls, no matter how hard they swim. This is the event horizon. Beyond it, even light can't climb back out. But here's where the analogy breaks down in an interesting way. In a real river, people watching from the shore see you go over the waterfall in finite time. With a black hole, the water, space-time itself, is moving so fast at the horizon that observers from the shore see you take infinite time to cross. But you, in the water, cross in finite time. The flow of time itself is different in different places. Now, let's get to the really uncomfortable question. What happens to the light after it crosses the event horizon? What's it doing in there? Is it bouncing around? Is it absorbed? Is it destroyed? The answer is going to challenge your concept of causality itself. Inside the event horizon, light is still moving at the speed of light. That's always true in its local frame of reference. But remember what I said. Inside the event horizon, all paths lead to the singularity. The light is moving toward the center. It has to, not because something is pulling it, but because the structure of spacetime only permits inward directions. Here's what's mind-bending. The singularity isn't a place in space. It's a moment in time. Inside the event horizon, the radial coordinate, what we'd normally think of as distance from the center, becomes time-like. The singularity is in your future, the way next Tuesday is in your future. You can't avoid going to next Tuesday. You can change what you do on Tuesday, but you can't prevent Tuesday from arriving. Similarly, once inside the horizon, you can change what trajectory you take to the singularity, but you can't prevent yourself from reaching it. The light beam, traveling inward, will reach the singularity. How long this takes depends on the size of the black hole. For a stellar mass black hole, maybe microseconds. For a supermassive black hole, maybe seconds or even minutes. But it will get there. And what happens at the singularity? This is where our physics breaks down completely. The singularity is a point where density becomes infinite, where space-time curvature becomes infinite, where all our equations start spitting out infinities and meaningless answers. Roger Penrose proved in 1965 work, for which he won the Nobel Prize in Physics in 2020, that singularities are an inevitable consequence of general relativity under realistic conditions. They're not mathematical artifacts. They're real predictions. But infinite density is almost certainly physics' way of saying, I don't know what happens here. Most physicists believe that when we develop a theory of quantum gravity, a theory that unites general Relativity with quantum mechanics, the singularity will be resolved into something else. Maybe the matter and energy reach a final, finite density, but one that's far beyond anything we can test. Maybe they tunnel into a baby universe. Maybe they evaporate through quantum processes we don't understand yet. But according to classical general relativity, the light reaches the singularity. And, well, that's the end of its story. It's not going anywhere else. It's not coming back out. The singularity is a one-way destination in time. Now, hold on. Before you think you understand what's happening, I need to tell you about something discovered by Stephen Hawking in 1974 that changes everything we've just discussed. And I mean everything. Because it turns out that black holes aren't quite black. They glow. And in glowing, they evaporate. And if black holes evaporate, where does the information about that light go? What I'm about to reveal to you is called the black hole information paradox, and it's one of the most profound unsolved mysteries in physics. It touches on the foundations of quantum mechanics, the nature of information, and what it means for something to exist. And yes, it's going to get weird. Stay with me. In 1974, Stephen Hawking was a young physicist at Cambridge working on combining quantum field theory with general relativity. He was looking at what happens to quantum fields in curved spacetime, specifically near the event horizon of a black hole. What he discovered shocked even him. According to quantum mechanics, empty space isn't really empty. It's seething with virtual particles, particle-antiparticle pairs that pop into existence, exist for a tiny fraction of a second, and then annihilate each other. This happens everywhere, all the time, but the particles exist for such a short time, and with such low energies that they don't normally have observable effects. But near the event horizon of a black hole, something remarkable happens. Occasionally, a particle-antiparticle pair will appear right at the horizon, with one particle just inside and one particle just outside. The particle that's outside can escape into space as real, detectable radiation. The particle that's inside falls toward the singularity. The net effect? The black hole loses a tiny bit of mass energy equivalent to the mass of the escaped particle and emits radiation into space. This is Hawking radiation, and it means black holes glow. They emit a thermal spectrum of radiation as if they were hot objects. But here's the kicker. Smaller black holes glow hotter and evaporate faster. A black hole with the mass of the sun would have a temperature of about 60 nanokelvins far colder than the cosmic microwave background, so it would actually absorb more energy than it radiates. Now, why does this matter for our light beam that fell into the black hole? Because if black holes evaporate, they eventually disappear completely. Every black hole, given enough time measured in googolls of years for stellar mass holes, but still finite time will evaporate into radiation and vanish. And here's the problem. Hawking radiation appears to be completely random thermal radiation, like the glow of a hot piece of metal. It doesn't encode information about what fell into the black hole. If you throw an encyclopedia into a black hole and wait for it to evaporate, the Hawking radiation that comes out appears to contain no information about what was in that encyclopedia. It's just random heat. But this violates a fundamental principle of quantum mechanics. Information is never destroyed. In quantum mechanics, if you know everything about a system at one time, you can calculate everything about it at any other time. The evolution is deterministic and reversible. If you burn a book, in principle, you could reconstruct the book by analyzing all the smoke particles, ash, and radiated heat with perfect precision. The information is scrambled, but not destroyed. Black holes seem to destroy information. You throw in an encyclopedia, you get back random thermal radiation. The information appears to be gone. This is the black hole information paradox. Think about what this means for your light beam. The light crosses the horizon, travels to the singularity, and apparently that's the end. But quantum mechanics says the information about that light, its wavelength, polarization, direction must be preserved somehow. As the black hole evaporates over inconceivable stretches of time, that information must come back out in the Hawking radiation. But how? The singularity is in the interior, causally disconnected from the exterior. Information at the singularity can't influence the Hawking radiation being emitted at the event horizon. So where is the information stored? How does it get out? For decades, this was considered perhaps the deepest problem in theoretical physics. Different physicists proposed different solutions. Maybe information is destroyed, and quantum mechanics needs to be modified. Hawking initially argued this. Maybe information is stored at the event horizon and slowly released in subtle correlations in the Hawking radiation, the holographic principle. Maybe black holes don't actually evaporate all the way, and information remains in a remnant. Maybe information is released in the final explosion when a black hole evaporates completely. In recent years, a consensus has started to form around something radical. The information never really enters the black hole in the first place, not in the way we think. This involves ideas called black hole complementarity and A equals EPR, which are some of the most brain-melting concepts in modern physics. Here's the basic idea. Remember how I said what happens depends on perspective. When you watch something fall into a black hole, you see it slow down and freeze at the horizon, red shifted into oblivion. From your perspective, it never really goes in it, gets smeared across the horizon as a super-thin hologram, encoded in the microscopic structure of the horizon itself. From the perspective of the infalling observer, they cross the horizon and continue inward. Both stories are true. But here's the wild part. These two perspectives can never be compared. You can't jump into the black hole to verify what the infalling observer saw, because once you do, you're infalling too. There's no way for the outside universe and the inside universe to compare notes. The two descriptions never come into conflict, so both can be true. The information about the light is stored in subtle correlations at the horizon, encoded holographically and slowly released in the Hawking radiation over time. The light that falls to the singularity in one description never falls in according to another description. Both are real. This is what it means to live in a quantum universe. Now, if your brain feels like it's melting, good. That means you're following along. We've just covered how light both does and doesn't fall into black holes, depending on perspective, how information might be preserved in holographic form at the horizon, and how quantum mechanics forces us to accept that multiple contradictory stories can all be true. But we're about to go deeper, because I haven't told you yet about what happens when black holes spin. And I haven't told you about the structure inside the horizon that could, in theory, allow light to do something truly impossible. What if I told you that inside certain black holes, light might not be destroyed at all? What if I told you about the inner horizon, the Cauchy horizon, and regions where causality itself breaks down? Hit that subscribe button, because we're about to enter the stranger-than-fiction realm of rotating black holes and the bizarre structures hiding inside them. Everything I've told you so far has been about the simplest kind of black hole. A non-rotating, uncharged, spherically symmetric black hole. This is called a Schwarzschild black hole. But realistic black holes aren't like this. Stars spin. When they collapse, conservation of angular momentum means the resulting black hole spins too. And a spinning black hole called a Kerr black hole, after Roy Kerr, who solved Einstein's equations for this case in 1963, is a completely different beast. First, a spinning black hole isn't spherical. It's oblate, squashed like a pumpkin, wider at the equator than at the poles. Second, and more importantly, it has two event horizons. An outer event horizon and an inner event horizon, also called the Cauchy horizon. And between these two horizons is a region called the ergosphere, where space-time itself is being dragged around the black hole. In the ergosphere, nothing can stay still, not even light. Space itself is rotating with the black hole, so fast that everything is swept around in the direction of rotation. This is called frame dragging, and it's one of the most bizarre predictions of general relativity. Light trying to move against the rotation is like a swimmer trying to stay still in a river flowing faster than they can swim. But here's where it gets truly wild. Because you can extract energy from a rotating black hole, this is called the Penrose process, discovered by Roger Penrose in 1969. Here's how it works. You drop an object into the ergosphere on a carefully chosen trajectory. Just before it crosses the event horizon, you split it into two pieces. One piece falls into the black hole. The other piece escapes back out, but with more energy than the original object had. Where did that extra energy come from? From the black hole's rotation. The piece that fell in had negative energy relative to an external observer. Yes, negative energy is possible in the ergosphere due to the frame dragging. When it falls in, it decreases the black hole's mass and spin. The piece that escapes gains that energy. You've literally extracted rotational energy from the black hole. Astrophysicists think this might be happening naturally around spinning black holes in the form of jets, massive beams of plasma and radiation shot out, perpendicular to the black hole's spin axis at nearly the speed of light. These jets, which can extend for millions of light years, might be powered by the black hole's rotation through magnetic field interactions that naturally implement the Penrose process. Now, let's talk about what happens to light inside a rotating black hole, because this is where physics enters the realm of science fiction, except it's not fiction. It's what the equations tell us, even if we're not sure these features could exist in reality. Once you cross the outer event horizon of a spinning black hole, you're inside, no escape is possible. But unlike a Schwarzschild black hole, you don't immediately begin falling toward a point singularity. Instead, the singularity in a Kerr black hole is a ring singularity, a circle in space. And the path inward is more complicated. As you fall inward past the outer horizon, you'd eventually reach the inner horizon, the Cauchy horizon. This is where things get mathematically weird. Past the Cauchy horizon, in principle, the structure of spacetime allows for some truly strange possibilities. In some trajectories, you could avoid the ring singularity entirely by passing through its center. The equations suggest regions of negative curvature where repulsive gravitational effects might exist. Most bizarrely, the equations predict closed time-like curves paths through spacetime that loop back on themselves, potentially allowing time travel. But here's the critical caveat. Most physicists think the inner horizon is unstable in practice. Remember how, from an outside perspective, matter falling into a black hole appears to freeze at the outer horizon? All that matter from the entire history of the black hole's formation until now is piled up at the outer horizon in a super-compressed, super-energetic shell. An observer crossing the outer horizon moving inward would encounter this entire history in a finite time. By the time you approach the inner horizon, you'd be hitting this blue shifted shell of radiation, all the light and matter from the entire lifetime of the black hole compressed into an infinitely energetic wall of destruction. This is called the mass inflation instability, and it was described by Poisson and Israel in 1990. The inner horizon isn't a stable surface you can cross. It's more like a wall of infinite energy that destroys anything approaching it. So for our light beam falling into a realistic, astrophysical spinning black hole, it crosses the outer horizon, propagates inward, and encounters this mass inflation region, where it's bombarded by all the blue shifted energy from everything that ever fell in before. It's not so much destroyed at the singularity as it's destroyed just inside the outer horizon. But the mathematical fact remains: the equations of general relativity, taken at face value, predict these bizarre inner structures. Whether they exist in physical black holes is an open question that only a theory of quantum gravity might resolve. Here's what should blow your mind right now. Inside a rotating black hole, the light we're tracking, the light that in one description is frozen at the horizon, In another description has reached the singularity, and in yet another is being torn apart by infinite energy. All of these descriptions are true depending on what variables you choose, what coordinates you use, what perspective you adopt. There is no single story of what happens to light in a black hole. Reality at this level isn't a single narrative. It's a superposition of narratives, each valid in its own framework, each telling a different story, none of them more real than the others. And we're not done, because we haven't talked about what quantum mechanics does to this picture. We haven't discussed what happens at the singularity from a quantum perspective. And we definitely haven't talked about what some cutting-edge theories predict, that the singularity might be a gateway to something else entirely. Take a breath. Seriously. What you've just learned would take most people years of physics education to encounter. You now understand frame dragging, the Penrose process, ring singularities, and the mass inflation instability. You understand why the interior of a black hole is more complex than almost any sci-fi writer imagines. But we're about to push even further, because everything we've discussed so far treats light as a classical wave or particle. We haven't brought quantum mechanics into the black hole interior yet, and when we do, the story gets even stranger. There are theories that suggest the singularity might not be an endpoint at all. It might be a transition point. Before we continue, leave a comment. Has your understanding of black holes changed yet? Because it's about to change even more. So far, we've been treating light as it's described by general relativity, a classical wave propagating through curved spacetime. But light is quantum mechanical. It comes in discrete packets called photons. And when we try to understand what happens to a photon inside a black hole quantum mechanically, we run into some of the deepest unsolved problems in physics. The fundamental issue is this: we don't have a complete theory of quantum gravity. General relativity works brilliantly for large-scale structures, curved spacetime, and black holes. Quantum mechanics works brilliantly for tiny scales, particles, and atoms. But we don't have a theory that unifies them, that works when spacetime curvature becomes extreme at small scales, which is exactly what happens at a black hole singularity. String theory, loop quantum gravity, causal set theory. These are attempts to build such a theory, but none are proven or complete. So when we ask, what happens to a photon at the singularity? We're asking a question that requires physics we don't have yet. But we can make educated guesses based on what quantum mechanics tells us. One principle that might apply is called complementarity in quantum mechanics, the idea that quantum systems can't be described by a single picture. You need multiple complementary descriptions. We've already seen this with wave-particle duality. Light is both a wave and a particle, depending on what experiment you do. Black hole complementarity, proposed by Leonard Susskind, Gerard T. Hooft, and others in the 1990s, extends this idea. It says that there are multiple complementary descriptions of what happens at a black hole. The infalling observer's description. They cross the horizon, observe nothing special there, continue inward, and eventually reach the singularity. From their perspective, information falls into the black hole. The external observer's description. Nothing ever quite crosses the horizon. Instead, information is scrambled and encoded on the horizon surface, then slowly released in Hawking radiation as the black hole evaporates. From this perspective, information never enters the black hole. These two descriptions seem contradictory. How can information both fall into the singularity and remain at the horizon? But complementarity says both are true, and the contradiction never becomes a problem because no single observer can access both perspectives. You can't verify what the infalling observer saw, because once you jump in to check, you're infalling too. This leads to an even more radical idea called the holographic principle, pioneered by T. Hooft and Susskind in the 1990s and given mathematical rigor through the ADS-CFT correspondence discovered by Juan Maldacena. In 1997, work that many believe deserves a Nobel Prize. The holographic principle states that all the information contained in a volume of space can be encoded on the boundary of that space. Think about a hologram on a credit card, a two-dimensional surface that encodes a three-dimensional image. The holographic principle suggests the universe works similarly. All the information inside a black hole, every particle, every photon, every bit of data can be encoded on the two-dimensional event horizon. This isn't just a metaphor. In certain mathematical models of spacetime, specifically anti-de Sitter space, physicists have proven that a theory of gravity in the interior volume is exactly equivalent to a quantum field theory on the boundary. The three-dimensional interior with gravity is a hologram emerging from the two-dimensional boundary with no gravity. They're different descriptions of the same thing. If this applies to real black holes, and there's active debate about this, then your photon falling into the black hole is simultaneously a particle propagating through three-dimensional curved space toward a singularity, and also information encoded in the two-dimensional structure of the event horizon. Both descriptions are equally real. Now, let's talk about what quantum mechanics might do to the singularity itself. Remember, the singularity is where density and space-time curvature become infinite according to classical general relativity. But quantum mechanics hates infinities. Whenever an infinity appears in quantum mechanics, it's usually a sign that the theory is breaking down and new physics is needed. Several theories suggest that quantum effects become important before you reach the classical singularity, and these effects might resolve the singularity into something finite. Loop quantum gravity suggests that space-time itself is quantized. It comes in discrete chunks. Just as you can't have half a photon, you can't have space-time curvature below a certain minimum scale, the Planck length, about 10 to 35 meters. In this theory, the singularity is replaced by a Planck star, a region of extremely high but finite density, where quantum gravitational repulsion prevents further collapse. String theory suggests that at extreme energies, the fundamental objects aren't point particles, but tiny vibrating strings. When strings approach each other at distances comparable to the string length, new physics kicks in that might prevent singular behavior. Some theories suggest that what we perceive as a singularity might actually be a quantum transition to another state, maybe a new region of spacetime, maybe even another universe. Here's a truly mind-bending possibility that emerges from some of these quantum gravity approaches. Maybe the photon doesn't end at the singularity. Maybe it passes through to something else. This is highly speculative, but let me explain the idea. In general relativity, the maximal extension of a black hole solution includes not just the black hole, but also a white hole, a time-reversed black hole from which things can only exit, not enter, and a connection between them through the interior. This is the Einstein-Rosen bridge, sometimes called a wormhole. In the classical theory, this connection pinches off too quickly for anything to pass through. You'd hit the singularity before reaching the other side. But some quantum gravity theories suggest that quantum effects might stabilize this connection, at least temporarily. If so, a photon falling into the black hole might not hit a singularity at all. Instead, it might traverse a quantum-smooth region of extreme space-time curvature and emerge somewhere else. Another part of our universe, another time, maybe even another universe entirely. This is not mainstream physics. It's speculative research at the cutting edge. But it's based on real mathematical physics, not just imagination. The key point is this: we don't know what happens at the singularity, and some of our best theories suggest it might not be an endpoint at all. At this point, you might be wondering, is any of this testable? Is it just mathematical philosophy? Or can we actually observe something about light and black holes that confirms or challenges these ideas? The answer is yes, and in the last few years, we've entered a golden age of black hole observation. In 2015, a LIGO collaboration detected gravitational waves from merging black holes for the first time, confirming that black holes exist and behave exactly as general relativity predicts. The signal matched the predicted waveform of two black holes spiraling together and merging curved, spacetime itself rippling outward at the speed of light. For this discovery, Rainer Weiss, Barry Barish, and Kip Thorne received the Nobel Prize in Physics in 2017. But even more relevant to our question about light, in 2019, the Event Horizon Telescope collaboration released the first image of a black hole's event horizon specifically, the supermassive black hole at the center of the galaxy M87, about 55 million light-years away. What they imaged was the shadow of the black hole surrounded by a ring of glowing light. Let me explain what you're seeing in that famous image, because it's directly relevant to our question. The black central region isn't actually the event horizon itself. It's larger, about 2.5 times the size of the event horizon. This is the black hole's shadow, the region from which light cannot reach us, either because it fell into the black hole or because it's trapped in orbit around the black hole. The bright ring around the shadow is light from the accretion disk hot gas spiraling into the black hole at relativistic speeds, heated to billions of degrees by friction and magnetic fields. Some of this light is emitted directly toward us. But here's what's wild. Some of the light from behind the black hole is bent around the black hole by gravitational lensing and reaches us. We're seeing light from both sides of the accretion disk simultaneously. Even more remarkably, there's a thin, bright ring right at the inner edge of the shadow called the photon ring. This is light that's orbiting. The black hole photons traveling in circular or spiral paths around the black hole, some making multiple orbits before either escaping or falling in. These are photons at the absolute edge of being captured. The 2019 image was of M87*. In 2022, the Event Horizon Telescope released an image of Sagittarius A, SGRA*, the supermassive black hole at the center of our own Milky Way galaxy, about 27,000 light-years away, with a mass of about 4 million suns. This was actually harder to image than M87*, because SGRA* is much smaller, and the hot gas around it swirls around in minutes rather than days. So they had to develop new techniques to combine data. Both images match the predictions of general relativity remarkably well. The size of the shadow, the brightness distribution, the asymmetry, brighter on one side, due to relativistic beaming from the rotating accretion disk. Everything matches. We are seeing, in real electromagnetic radiation captured by light that escaped, the signature of spacetime so curved that even light can barely escape. And here's the haunting part. For every photon that escaped and traveled across the universe to form that image, there were countless photons that crossed the event horizon instead. Right now, at this very moment, photons are falling into SGRA*, experiencing the journey we've been discussing frozen at the horizon from our perspective, traveling inward toward the singularity from their own perspective, their information potentially preserved in holographic form, and slowly being released in Hawking radiation over timescales longer than the age of the universe. We need to talk about entropy, because it connects to perhaps the deepest aspect of what happens to light inside a black hole, the information it carries. Entropy, in physics, measures disorder or uncertainty, or the amount of information needed to describe a system. And black holes have a profound connection to entropy that revolutionized our understanding of information itself. In the early 1970s, Jacob Bekenstein was a graduate student working with John Wheeler. He was troubled by what happens when you drop a hot cup of tea into a black hole. The tea has entropy thermal energy, molecular disorder. Black holes were thought to be completely characterized by just 3 numbers: mass, spin, and electric charge. Everything else about what falls in is lost. So when you drop the tea into the black hole, the tea's entropy seems to disappear, violating the second law of thermodynamics, which says total entropy never decreases. Bekenstein proposed something radical. Black holes themselves have entropy, proportional to the area of their event horizon. When you drop the T in, the black hole's horizon area increases, and the black hole's entropy increases by more than the entropy lost, preserving the second law. The formula is beautiful and profound. The entropy of a black hole equals 1/4 of its horizon area, measured in Planck units. This is the Bekenstein-Hawking entropy formula. What makes it remarkable is that entropy is usually proportional to volume. The bigger a box of gas, the more microstates it can have, the more entropy. But black hole entropy is proportional to area. This was the first hint of the holographic principle that somehow the information inside a black hole is encoded on its two-dimensional surface. Every quarter of a Planck area on the event horizon corresponds to 1 bit of information. A solar mass black hole has a horizon area of about 1077 square Planck units, so it can store about 1077 bits of information, far more than the number of bits needed to describe all the particles in the observable universe. When Hawking discovered that black holes radiate, this gave physical meaning to black hole temperature, inversely proportional to mass, and confirmed that they really do have thermodynamic properties. A black hole is a thermodynamic system with temperature, entropy, and energy. It can be in thermal equilibrium with radiation. It obeys the laws of thermodynamics. So what does this mean for our photon? When the photon crosses the horizon, the black hole's mass increases by the photon's energy E equals mc, so energy has mass. The horizon area increases slightly for a single photon, an imperceptibly small amount. The black hole's entropy increases. The information carried by the photon, its frequency, polarization, direction, adds to the black hole's information content. But here's the key. If that information is encoded on the horizon, and if it's eventually released in the Hawking radiation, then the story of the photon isn't over when it crosses the horizon. It's just been reformatted, scrambled, encoded in the quantum structure of the horizon. And over unimaginable spans of time, as the black hole slowly evaporates, that information leaks back out in correlations in the Hawking radiation. Recent work by Hawking, Perry, and Strominger, 2016, and by Hawking and others, suggests that the information is stored in soft, Hare quantum states at the horizon that don't affect the classical properties of the black hole, but do encode information. Other work focuses on quantum entanglement between the Hawking radiation and the black hole interior, showing how information can be preserved even though the radiation appears thermal. Let me give you an analogy for information preservation. Imagine you write a message, put it in a box, and burn the box. The message seems destroyed. But in principle, if you had perfect knowledge of every smoke particle, every ash fragment, every photon of thermal radiation, you could reconstruct the message. The information is scrambled beyond any practical recovery, but it's not destroyed, it's encoded in subtle correlations. Black holes do something similar, but more extreme. The information is scrambled in the most complex way possible, encoded in quantum correlations at the horizon, and released gradually in radiation that appears random, but contains the information in deeply buried correlations. Recovering it would require collecting every Hawking radiation photon the black hole ever emits, measuring them with impossible precision, and performing computations beyond the capacity of any conceivable computer. But in principle, it's there. Your photon's information, the exact details of its quantum state, joins the black hole's information content, becomes part of the holographic encoding on the horizon, and eventually is released. The photon as a distinct entity is gone, but its information lives on, transformed beyond recognition, but preserved according to the fundamental laws of quantum mechanics. Let's take a moment to recognize what you've just learned. You now understand the Bekenstein-Hawking entropy formula, the connection between black holes and thermodynamics, and why information must be preserved even when it falls into a black hole. You understand that your photon story might not end at the singularity. It might be transformed into quantum information, encoded on the horizon, and eventually released. If you're still with me, you're part of a small group of people who followed this journey to the cutting edge of human knowledge. Hit that like button if your mind is sufficiently blown. And drop a comment. What's the most surprising thing you've learned so far? Because we're not done. We still need to talk about what all of this means. Not just for light or photons, but for you, for consciousness, for time, for what it means to exist in a universe where black holes are real. The personal connection is coming, and it's going to reframe everything. Let's return to something I mentioned at the beginning, but didn't fully explore. Light doesn't experience time. For a photon, the universe is frozen. And understanding this deeply will help you grasp something profound about what happens inside a black hole. Special relativity tells us that as you move faster through space, you move slower through time. This is time dilation. Astronauts on the International Station, moving at about 28,000 kilometers per hour, age about 0.01 seconds less per year than people on Earth. At 86% of light speed, time runs at half speed 1 year for you, equals 2 years for a stationary observer. At 99.5% of light speed, time runs at 1/10 speed. At exactly light speed, the dilation factor becomes infinite. Time stops. But this creates a logical problem. What does it mean for time to stop? You can't have experiences, thoughts, or changes without time. So what's it like to be a photon? The answer is that the question is malformed. Photons don't have a reference frame. The mathematics of special relativity breaks down when you try to transform to a light speed frame. It's not that we don't know what a photon experiences. It's that experience doesn't apply. A photon doesn't have a perspective in the usual sense. But here's a useful way to think about it. From the photon's perspective, and I'm using that term loosely, its creation and absorption are simultaneous events at the same location. The 10 billion light years it travels from a distant galaxy to your eye happen at zero distance and zero time from its perspective. It's created and destroyed in the same instant at the same place. This has profound implications for black holes. When we say light falls into a black hole, we're describing this from our perspective, where the light has extension in space and duration in time. But from the light's perspective, all of its journey from emission to crossing the horizon to reaching the singularity is a single instantaneous event. Now combine this with what we learned about time dilation near black holes. As light approaches the event horizon from an outside perspective, time for that light slows down. At the horizon, it stops. But from the light's perspective, there's no time to slow down. It's already at zero. This creates a strange dual picture. The outside universe sees the light redshifted and frozen at the horizon forever. The light, in its non-time experiencing way, reaches the singularity instantly. Neither perspective is more correct. They're complementary descriptions of the same event viewed from different reference frames. And here's what's deeply weird. You can apply this to anything falling into a black hole, not just light. If you fell in, you'd experience crossing the horizon and reaching the singularity in finite proper time measured by a clock you're carrying. But an outside observer would never see you cross. From their perspective, you're frozen at the horizon, your image red shifting into darkness, your information encoded on the surface forever. Which is real? Both. The universe doesn't have a single reference frame. Reality is the collection of all these perspectives, each valid in its own frame, together forming a complete picture that transcends any single viewpoint. Let me give you something to really ponder. Every massless particle, not just photons, experiences zero proper time. Gravitons, if they exist, would be massless. They would mediate the gravitational force at light speed, experiencing no time. Gluons, which mediate the strong nuclear force, are massless and experience no time. In a sense, all the fundamental forces, except possibly gravity. If gravitons are massive in some theories, are mediated by particles that don't experience time. The fabric of causality itself, how one event influences another, is woven by particles for which all of time is a single instant. The universe, at its deepest level, might be timeless. Time is something that emerges from massive particles like us that move slower than light. We're embedded in a framework where time flows, but the fundamental interactions that make up reality occur in a timeless way. Black holes reveal this structure because they're places where the usual distinctions between space and time break down. Inside the horizon, the radial direction becomes time. Your future is toward the singularity. Time and space have traded roles. The universe is telling us that these concepts aren't as separate or absolute as they appear in everyday life. We touched on entropy earlier, but we need to go deeper because the connection between black holes and thermodynamics is one of the most beautiful and mysterious discoveries in physics. It suggests that black holes aren't just gravitational objects, they're the most efficient information storage and processing systems possible in our universe. The 4 laws of black hole mechanics, developed by Bardeen, Carter, and Hawking in the early 1970s, have exact parallels to the 4 laws of thermodynamics. The zeroth law. The surface gravity is constant over the event horizon of a stationary black hole, just as temperature is constant in thermodynamic equilibrium. The first law. Changes in the black hole's mass are related to changes in area, angular momentum, and charge, just as energy change relates to heat, work, and other thermodynamic quantities. The second law. The total area of event horizons never decreases, just as total entropy never decreases. The third law. The surface gravity cannot be reduced to zero in a finite number of steps. When these laws were first discovered, physicists thought they were just mathematical analogies. Black holes aren't really hot, right? They don't really have entropy. They just behave as if they do. But then Hawking discovered that black holes radiate, and the temperature calculated from that radiation exactly matched the temperature implied by the mathematical analogy. Black holes literally are hot. They literally have entropy. The analogy is real. This leads to something profound. Black holes might be the key to understanding the deep nature of spacetime itself. If black holes have entropy, and entropy counts microstates, the number of ways the fundamental constituents can be arranged to produce the same macroscopic appearance, then the event horizon must have microscopic structure. Spacetime must be made of something at the smallest scales. In string theory, this something is strings and brains. Calculations by Strominger and Vafa in 1996 showed that you can count the quantum states of certain black holes in string theory and get exactly the Bekenstein-Hawking entropy. This was one of the first big successes of string theory reproducing a result from classical general relativity by counting quantum states. In loop quantum gravity, space-time is woven from quantum threads of space itself, and the horizon consists of punctures, where these threads intersect the surface. Counting these punctures gives the Bekenstein-Hawking entropy with a specific value for a constant that was previously undetermined. Now, let's connect this to our photon. When the photon crosses the horizon, it adds energy to the black hole, increasing the mass. By E equals mc, this increases the horizon area. By the entropy formula, this increases the entropy. The photon's information becomes part of the microstructure of the horizon. But what is that microstructure? We don't know for certain. It might be quantum strings vibrating in complex patterns. It might be quantum loops of space tangled in specific configurations. It might be qubits of information encoded in quantum fields at the horizon. Different approaches to quantum gravity give different answers, but they all agree on the macroscopic result. The entropy increases in a specific, calculable way. This tells us something remarkable. When you ask, what happens to light inside a black hole? You're asking a question that touches the very foundations of spacetime. The answer requires understanding what space and time are made of at the deepest level. And we're tantalizingly close to figuring this out. Here's a thought that should make you pause. Your photon, carrying some tiny amount of information, adds to the black hole's entropy when it crosses the horizon. But the maximum entropy of any region of space is achieved when that region is filled by a black hole. Black holes are the densest possible repositories of information. This means that when a photon falls into a black hole, it's entering the most informationally dense environment possible. Every bit of information that can fit in that volume of space is already there, encoded in the horizon's microstructure. Adding one more photon doesn't just add information, it pushes the system closer to the maximum possible entropy. And when the black hole evaporates through Hawking radiation, it's performing the most thorough information scrambling possible. The information is released in a form so deeply encrypted that it would take computational resources exceeding anything that could exist in our universe to decode it. The photon's information isn't destroyed, but it's been put through the universe's ultimate encryption algorithm. Let's step back and make sure you really understand the core concepts by using several different analogies. Because what happens inside a black hole is so far removed from everyday experience that we need multiple ways to think about it. Analogy 1. The waterfall. Imagine spacetime as a flowing river. Far from the black hole, the flow is gentle, you can swim against it. Light can escape. Near the black hole, the flow gets faster. At the event horizon, the flow equals the speed of light. Beyond that, even swimming at light speed can't get you back upstream. This captures the idea that inside the horizon, even light moving outward at full speed is actually moving inward because space itself is falling faster than light can climb. Analogy 2. The pitfall trap. Think of spacetime as having directions like up, down, north, south. Far from a black hole, all directions are available. At the horizon, the outward direction starts closing off. Inside the horizon, there is no outward direction anymore. All paths lead inward. It's like being inside a pitfall trap where the walls are perfectly smooth and vertical. No matter which way you push, you slide down. The geometry has eliminated the possibility of going up. Analogy 3. The movie theater. From outside the black hole, you watch events at the horizon, like a movie that's slowing down frame by frame, each frame taking longer to transition to the next until it effectively freezes. But for someone in the movie, the action continues normally. They cross the horizon without noticing anything special. You can't pause the movie to check if it's really frozen, because the moment you enter the theater to look, you're in the movie too, and it's running at normal speed from your perspective. Analogy 4. The information archive. Think of the event horizon as a two-dimensional hard drive where information is stored. When something falls in, from one perspective, it merges with this hard drive, its information encoded on the surface. From another perspective, it passes through the surface into a three-dimensional interior volume. But these aren't contradictory. The 3D interior is a hologram projected from the 2D surface. The information exists in both descriptions simultaneously. Analogy 5. The time boundary. Inside a black hole, the singularity is not a place, it's a time. Think of your future death. You can move around in space all you want, but you can't avoid moving forward in time toward that event. Similarly, inside a black hole, you can change your trajectory in space, but you can't avoid moving forward in time toward the singularity. It's in your future the way tomorrow is in your future, inevitable regardless of what actions you take. These analogies all capture different aspects of the truth, but none is perfect. That's because black holes involve space-time behaving in ways that have no parallel in everyday life. The mathematics is precise, but translating it into intuition requires multiple imperfect metaphors, each illuminating one facet of a multifaceted reality. When I say light falls into a black hole, I'm already using a metaphor gravity as something that pulls things down. But gravity and general relativity isn't a force. It's the curvature of spacetime. Objects follow the straightest possible paths through curved spacetime, and we perceive this as gravitational attraction. So a photon doesn't fall into a black hole because something pulls it. It moves on a straight path, a geodesic, through curved spacetime, and the curvature is such that all straight paths lead inward. The photon thinks it's going straight. Spacetime is curved such that straight leads to the singularity. Here's one more analogy that captures something important. Think of the universe as a book with pages representing different moments in time. For us, moving through time is like turning pages. We experience one page, then the next. For a photon, the entire book is a single page. It exists on multiple pages simultaneously from our perspective, traveling through space over time. But from its perspective, all those pages are the same page. When the photon enters a black hole, it's entering a section of the book where the pages are scrambled. The order isn't clear. Past, present, and future get mixed up. The singularity is like a point where all the pages converge. Every timeline ends there. This captures something of what it means for the singularity to be a moment in time rather than a place in space. It's not a location you could avoid by going a different direction. It's a moment you move toward inevitably, the same way you move toward next Tuesday. Now we're going to shift gears. You understand the physics, at least as much as anyone can without years of study. But what does it mean? What does it tell us about reality, about existence, about our place in the universe? First implication: perspective is fundamental. We've seen that what happens to light in a black hole depends on whose perspective you adopt. The external observer sees one story. The infalling observer sees another. The photon itself, if we could speak of its perspective, sees yet another. None of these perspectives is more real than the others. This is a profound departure from classical physics, where there was absolute space and absolute time, a God's eye view from which the truth could be told. Einstein demolished that with relativity, showing that time and space depend on motion. Black holes take this further, showing that even the question, did this event happen, can have different answers from different perspectives. What does this mean for you? It means that your experience of reality is a perspective, not the totality. Right now, you experience time flowing forward, space extending around you, events happening in a sequence. But this is your reference frame. Someone moving at a different speed experiences time differently. Someone in a different gravitational field experiences time differently. There is no universal now. When you say, right now, on a planet orbiting a star in another galaxy, something is happening, that sentence is almost meaningless. Right now, according to what reference frame? Depending on your motion, your now could correspond to their yesterday or their tomorrow. Present, past, and future are relative concepts. Black holes make this vivid because they create situations where these differences become extreme. The photon crosses the horizon in your far future, infinitely far, in fact, but in its own finite present. Both are correct. Reality accommodates multiple timelines simultaneously. Second implication: information is physical. The whole discussion of the information paradox, where the information goes when something falls into a black hole, shows that information isn't just a human concept. It's a physical quantity, as real as energy or momentum. Information has to be conserved because the universe is quantum mechanical, and quantum mechanics is fundamentally about information. When you learn something, physical changes occur in your brain. Information is encoded in the arrangement of neurons, the strengths of synapses, the patterns of connectivity. This isn't a metaphor. Your thoughts are physical states of matter. When the photon carries information into the black hole, that information doesn't cease to exist just because the photon is destroyed. It's transformed, encoded in the quantum state of the black hole, preserved in correlations that will eventually be released in Hawking radiation. Information is a conserved quantity like energy. Third implication: spacetime is not fundamental. The fact that black holes have entropy, that they behave thermodynamically, that their information can be encoded on a two-dimensional surface even though they occupy three-dimensional space, all of this suggests that spacetime is emergent. It's not the deepest level of reality. It's something that emerges from something more fundamental. Think of a picture on a computer screen. The picture looks continuous smooth colors, gradual transitions. But zoom in enough, and you see pixels, discrete units. The continuous picture emerges from discrete elements. Similarly, spacetime might emerge from discrete quantum information at the Planck scale. Several approaches to quantum gravity suggest this. In loop quantum gravity, space is woven from quantum threads. In string theory, spacetime emerges from the interactions of strings and branes. In causal set theory, spacetime is built from discrete causal relationships. In the holographic principle, three-dimensional space emerges from two-dimensional information. If spacetime is emergent, then asking what happens inside a black hole is like asking what happens inside a pixel. On a screen, the question assumes the pixel has an interior, when really it's just a discrete unit of information displaying a color. The question might be based on a category error. Fourth implication: the universe is connected in ways we can barely perceive. Quantum entanglement means that particles can be correlated across any distance instantaneously. The holographic principle suggests that information in a volume is encoded on its boundary. Black holes connect to thermodynamics, which connects to information theory, which connects to quantum mechanics. Your photon falling into the black hole becomes entangled with the quantum state of the black hole, which is entangled with the Hawking radiation that's been emitted, which is spreading throughout the universe. In a very real sense, that photon's information spreads across space and time, becoming part of the vast web of quantum correlations that underlies reality. You are part of this web too. Every particle in your body has been elsewhere, part of other systems, carrying other information. Particles don't have identity in quantum mechanics. An electron is not this electron versus that electron. It's just an electron, and any electron could swap with any other without changing anything. The apparent boundaries between objects are conventional, not fundamental. Fifth implication: the universe is stranger than we can imagine. I've thrown a lot of mind-bending concepts at you: time stopping, space falling, singularities being moments rather than places, information encoded holographically, complementary descriptions that seem contradictory, all being true. And here's the thing: this is all mainstream physics. This isn't speculation. This is our best understanding of how reality works. And we don't have all the answers. We don't know what happens at the singularity. We don't know if Hawking radiation preserves information exactly or approximately. We don't know if the interior of a black hole connects to anything else. We don't know what spacetime is made of at the deepest level. The universe has surprised us at every turn. When we developed quantum mechanics, we discovered that reality at small scales is probabilistic, not deterministic. When we developed relativity, we discovered that time and space are relative, not absolute. When we discovered Hawking radiation, we found that black holes glow. When we developed the holographic principle, we found that information in 3D space can be encoded in 2D. Every time we think we understand, we discover we're wrong in interesting ways. The universe is under no obligation to make sense to evolved primates on a small planet. The fact that we can understand anything at all is remarkable. Now let's bring this home. Why should you care about what happens to light inside a black hole? Second, it teaches you about the nature of time. You worry about the past mistakes made, opportunities missed, words spoken that can't be taken back. You worry about the future. Will things work out? What if something bad happens? Am I making the right choice? But past and future are relative concepts. The photon from a distant star that enters your eye left that star long ago from your perspective. But from the photon's perspective, it was created and absorbed in the same instant. The past isn't back there, somewhere. It's a relationship between events in spacetime. This doesn't mean the past doesn't matter, of course, it does. But it means that the present moment right now is all that exists in your reference frame. The past exists only as memory and evidence. The future exists only as possibility. Neither is more real than the other, and both are less real than now. Anxiety about past and future is natural and sometimes useful, but physics reminds us that they're constructs. The only time you ever exist is now. The photon exists only in its now, which encompasses its entire journey. You exist only in your now, which is this moment. Third, it teaches you about information and meaning. The photon carries information frequency, polarization, direction. When it falls into the black hole, that information isn't destroyed. It's transformed, scrambled, and coded differently. Eventually, it's released, though in a form so changed that you couldn't recognize it. Your life is similar. The experiences you have, the information you absorb, the thoughts you think these change you, become encoded in who you are. When you die, that information doesn't vanish from the universe. It persists in everyone you affected, every word you wrote, every action's consequences rippling through time. More than that, you are information. The pattern that makes you you, your memories, personality, thoughts, is information encoded in the physical structure of your brain. This isn't reductive. It's empowering. Information is preserved in quantum mechanics. The pattern that is you is real and significant, as real as the photon's wavelength, as significant as any physical quantity. Fourth, it teaches you about boundaries and identity. The event horizon seems like a clear boundary inside versus outside, trapped versus free. But we've seen that this boundary is observer-dependent. From outside, nothing ever quite crosses. From inside, you've already crossed and are continuing inward. The boundary is real, but also perspective-dependent. Your boundaries are similar. Where do you end and the external world begin? Your skin? Your breath is inside you, then outside, then inside someone else. Your cells are constantly dying and being replaced. You're mostly not made of the same atoms you were 7 years ago. Your thoughts are shaped by language, culture, and experiences from outside. Your actions affect others, rippling outward. The boundary of self is conventional, not fundamental. You're a pattern of information in constant exchange with the universe. Just as the photon becomes entangled with the black hole's quantum state, you're entangled with everyone and everything you interact with. Identity is relational, not absolute. Fifth, and perhaps most importantly, it teaches you that reality is ultimately mysterious, and that's okay. We can describe what happens to light mathematically. We can predict, test, verify. But understanding what it means, what it really means, intuitively, visually, experientially, is difficult or impossible because our intuitions evolved for everyday situations, not extreme physics. There's a temptation to think that because we can't fully visualize it, we don't understand it. But mathematics is a form of understanding. Accepting multiple complementary descriptions is a form of understanding. Recognizing the limits of intuition is a form of understanding. You live in a universe where light experiences no time, where space can fall faster than light can climb, where information is preserved even when it seems destroyed, where the same event takes both infinite and finite time depending on perspective. This is the universe you inhabit. And the fact that it's strange doesn't make it less real. It makes it more wondrous. Let's talk about what we still don't know, because the cutting edge of physics is where the most exciting questions live. What happens to light inside a black hole is not a fully solved problem. We have theories, predictions, and mathematical frameworks, but there are open questions that will occupy physicists for decades or centuries. First open question: what is the correct theory of quantum gravity? We need a theory that unifies general relativity and quantum mechanics to truly understand what happens at the singularity and at the Planck scale near the horizon. String theory, loop quantum gravity, causal dynamical triangulation, asymptotic safety. We have candidates, but no experimental evidence distinguishing them. Until we do, the deepest questions about black hole interiors remain theoretical. Some physicists are working on ways to test quantum gravity through very precise measurements. The next generation of gravitational wave detectors might be sensitive enough to detect quantum corrections to the black hole merger signal. Cosmic ray observations might reveal effects of Planck scale physics. It's a long shot, but physics has been surprised before. Second open question: how exactly is information preserved in Hawking radiation? We believe it must be preserved to avoid violating quantum mechanics, but the mechanism isn't fully understood. Recent work on the island formula by Onhiri, Engelhardt, Marolf, and Maxfield 2019 provides a mathematical framework for tracking information, suggesting that regions inside the horizon islands can contribute to the entropy of the radiation outside. This is cutting-edge research happening right now. Other approaches involve soft hair at the horizon quantum states that store information or subtle quantum entanglement between early and late radiation. Different approaches give different pictures, and it's not yet clear which is correct or if they're all describing the same physics in different languages. Understanding this fully would be revolutionary. It would tell us about the fundamental nature of spacetime, information, and quantum mechanics. It might lead to technologies we can't even imagine: quantum computation, information processing, or communication schemes based on principles we haven't discovered yet. Third open question: do black hole interiors connect to anything? The Einstein-Rosen bridge suggests a connection, but classically it pinches off. Quantum effects might stabilize it. Some theories propose that black holes connect to other regions of spacetime, or even other universes. The firewall paradox, proposed by Onhiri, Marolf, Palczynski, and Sully in 2012, suggests that infalling observers might encounter a wall of high-energy radiation at the horizon, contradicting the equivalence principle. This paradox hasn't been fully resolved. Different physicists favor different resolutions. Complementarity: the firewall only appears from the outside perspective. A equals EPR, entanglement creates wormholes. Quantum error correction: the black hole interior is a quantum code, or modifications to how we think about horizons. If black holes do connect to other regions, the implications are staggering. Wormholes, time travel, parallel universes concepts from science fiction might have real physical manifestations in black hole interiors. We might never be able to verify this directly, but mathematics hints at possibilities beyond our wildest dreams. Fourth open question: can we simulate black hole interiors? Quantum computers might eventually be powerful enough to simulate the quantum state of a black hole and track information through Hawking radiation. This would be an experimental test of our theories without actually creating a black hole. Researchers have already created analog black holes in laboratory systems with event horizons for sound or light in certain materials. These don't have real singularities, but they have horizons, and we can study how waves behave near them. Some experiments have even detected analog Hawking radiation quantum fluctuations, creating pairs of phonons at the acoustic horizon, with one escaping and one trapped. These analogs won't answer every question about real black holes, but they're proof of concept. They show that horizon dynamics and Hawking-like radiation are robust features, not mathematical artifacts. As our technology improves, we might create more sophisticated analogs that teach us about quantum gravity. Fifth open question: what can black holes teach us about cosmology? The entire observable universe might be inside something like a black hole. Our universe is expanding, and in some models, it's the time-reversed version of a black hole collapse, white hole, from which matter pours out rather than in. Some cosmological models propose that our Big Bang was the interior of a black hole in another universe. And when black holes form in our universe, they create new universes inside them. This is the Lee-Smolin-Feekant universe hypothesis, natural selection for universes, with physical constants tuned by which universes produce more black holes. This is speculative but based on real physics. The mathematics of black hole interiors and cosmological expansion have similarities. Understanding one might illuminate the other. Questions about what happens to light inside a black hole might connect to questions about the origin and fate of the universe itself. We've journeyed deep. You've learned about event horizons, time dilation, frame dragging, ring singularities, Hawking radiation, information paradoxes, entropy, holography, quantum gravity, and the frontiers of physics. You've seen how light both does and doesn't fall into black holes depending on perspective. You've grappled with ideas that challenge your intuitions about time, space, and reality. So let me give you the ultimate answer to the question: what happens to light inside a black hole? The answer is, it depends on what you mean by happens, light, and inside. If by what happens, you mean, what does an outside observer see? The answer is, the light redshifts asymptotically toward the horizon, taking infinite time to cross, its information preserved holographically on the horizon surface, and eventually released in Hawking radiation over timescales far exceeding the current age of the universe. If by what happens you mean, what does an observer falling with the light experience? The answer is, the light crosses the horizon in finite time, propagates through the curved interior spacetime, and reaches either a singularity where physics breaks down or a quantum-resolved region where something happens that our current theories can't fully describe. If by light you mean classical electromagnetic waves, the answer involves geodesics through curved spacetime leading inevitably inward. If by light you mean quantum photons, the answer involves entanglement with the black hole's quantum state and eventual information recovery through Hawking radiation. If by inside you mean beyond the event horizon in the conventional sense, there is an interior region that exists from the infalling perspective, but not from the external perspective. And this complementarity is fundamental, not a flaw in our understanding. The deepest answer is this: light doesn't experience time. From the photon's timeless perspective, creation and destruction are the same event. The journey from emission to absorption, whether that absorption happens in your eye or in a black hole singularity, is instantaneous. The photon exists in a superposition of being here and there, now and then, outside and inside, frozen and falling until observed from a particular reference frame, which collapses the quantum state into one of these complementary descriptions. The universe has no obligation to provide a single story. Reality at this level is inherently perspectival. What happens to light inside a black hole is whatever happens from your chosen reference frame, and all reference frames are equally valid. The complete truth is the collection of all these partial truths. This isn't uncertainty or ignorance. This is the structure of reality itself. The universe is quantum mechanical and relativistic, and these theories tell us that reality is contextual, relational, and perspectival at the deepest level. There is no view from nowhere. Every answer is an answer from somewhere. And here's the beautiful part. This applies to everything, not just black holes. Right now, light from the screen in front of you is entering your eyes. Photons are being absorbed by molecules in your retina, triggering chemical changes that send electrical signals to your brain, creating the experience of vision. Those photons didn't experience the journey from screen to eye for them. Emission and absorption were simultaneous. But for you, there was a journey, a duration, an experience. The universe is like this vast collections of perspectives, each valid, each partial, together forming something too large for any single viewpoint to encompass. Your one perspective in this vastness, what you see, is real. But it's not all of reality. There are countless other perspectives, other ways of seeing, other valid stories being told. Light falling into a black hole tells countless stories, frozen at the horizon, reaching the singularity, encoded holographically, released in radiation, destroyed, preserved, inside, outside. All true, all partial, all aspects of a reality richer and stranger than language can capture. Let me end with this. You've spent over 3 hours thinking about light and black holes. Why? Because there's something in the human spirit that wants to understand. That understanding is never complete, but it's real, and it matters. Because understanding connects you to something larger than yourself. It places you in a tradition of inquiry, stretching back to ancient philosophers and forward to future scientists. It makes you a participant in humanity's greatest project, comprehending the cosmos. What happens to light inside a black hole? It becomes part of the mystery. It adds to the entropy. It carries information into the unknown. It teaches us humility and wonder. And it reminds us that reality is deeper, stranger, and more beautiful than we ever imagined. Now go outside, look up at the night sky, and know that photons are traveling from distant stars to your eyes, carrying information across space and time, connecting you to the universe. Some of those photons passed near black holes on their journey. Some were emitted by stars that have since collapsed into black holes. You're looking at light from the past, seeing the universe as it was. All those perspectives folded into this moment of seeing.